All right, this is part 8 of the join video for a universal joint. Basically, a universal joint in Dyna is created by set up two different rotation axes, where point 1 and 2 forms the center, point 3 and such that 1, 3 forms one axis, and point 4 such that 2, 4 forms another axis. Basically, it allows two node sets to rotate relative to each other along two different rotation axes. So if you can imagine the inside diameter so the inside surface of the disk right there can rotate, right? You will be able to rotate along one of the axes versus then another, basically, and that's how the Revolut joint itself, a universal joint itself works. So to do this, doing it exactly the same way as before, you require four different points. Point one and two are coincident. Point three is gonna basically form the z-axis, as you can see here. It's only different along the z-axis. And point four is such that it's only different along the y-axis. So you form the rotation axis, one along z, one along y. This is a geometric definition, right? So you can sort of see that's a center point, which has two different points coincident. Point three forms along the one of the rotation axis. Point four forms another the rotation axis. And this is what the joint is gonna look like once you set it up. I only rotated one of them because it's kind of hard to do it both. But it's a good way to look at it. Okay, so a quick setup for this model, right? I'm actually gonna get rid of the center block because I don't need it. Center block is mostly just for sort of evaluating, right? And then what I can do here is I'm gonna call this piece part 1, and I'm gonna call this piece part 2. And then what we can do here, right? Obviously, I'm gonna suppress this. I don't need that. And then in a situation like this, which is kind of interesting, what we want to do, maybe I'll unsuppress this for now because what I kind of want to do is to find my center point, which is the center point on my rotation axis. So what I want to do here is I'm gonna go ahead and select these, and you can see that right there becomes my center point. And then instead of using geometric definition, I'm gonna change that to the global coordinate system, which gives me my point number 1. Okay, and then now I can suppress this. And for the other point, right, you can sort of see point 1, this is point 1. Point 2 is going to be coincident, so I'm just going to duplicate it. I'm going to call this point 2. Point 3 is going to be different only along one of the axes, which in this case I'm going to say it's going to be different along the z-axis, which I'm going to change the number to, say, negative 31.775, which is what I had before. Okay, and then for point 4, it's going to be different along the y-axis, right? And then along the y-axis, I'm going to do positive 31.74. And you can sort of see with these 4 points, what you have is you have one axis here and one axis here. And then the first point are two different points that's going to be centered together at the same time. Okay, so once we have that, all we have to do is just select our nodes, right? So what we do here, I'm just going to select all the inside faces. I'm going to call this inside 1. And I'm going to call these inside 2. Okay, and then now once we have these, I'm going to first of all let's mesh this. I guess let's go ahead and just mesh this. I think a 2mm is okay. Okay, and then let's go ahead and generate node set. Generate node set. Alright, I'm gonna call this 9001. I'm gonna call this 9002. Okay, I can sort of see now these two node sets are going to form a kinematic relationship through two CNRBs, like we've done this for all the other videos for the joints, right? So let's go ahead and do that. Let's go ahead and add a command object. And then what I will do here is I'll just go ahead and copy this whole thing over. This is my basically template. So you can see 6.35, 12.7, negative 0.27, which is my first 2 points. Right, and then the 6.35, 12.7, negative 31.75, that's my third point. And then this is right here, which is putting the 31.75 on the center. That's going to be my fourth point. And the other 2 points are left blank. And this is going to form my constrained joint, COR, universal. Right, you see this universal card right here. It's going to basically create a kinematic constraint along CNRBs 8001, 8002, which are tied to these two node sets. which means these two node sets are going to have a kinematic constraint follow the universal joint. All right, once we've done that, let's go ahead and add some simple constraint to test up the model, right? So I can add a fixed support here, and then I can then add a remote displacement on the other end. If you want, maybe you can do this whole thing across this whole. Let's just do it like this, which is good. And then from here, right, you can just set this to the center point right there. And then let's say because you can rotate along Z, it can rotate along Y, right? What we can do is just to set up some rotation constraint, like say 120 degree this way, right, which is going to rotate along Z. And then if you want to rotate along Y, which makes more sense if you do it on this side, so you just fix on this end and rotate along Y on the other end, which should work. And it is an interesting joint to test out more. Test out, like for example, if I haven't tried it out yet, like what happens if I put a Y rotation on this surface as well? Is it gonna go through a Y like you do in Z, which I think is possible, right? But this is a much better way to do so. Essentially setting up a joint such as this. And then let's go ahead and set up to rigid. And this basically sets up the model. And if you want to be strict, let's go ahead and get rid of my control cards and get rid of my database cards. And then let's add a joint, which is for my joint forces and my D3 plots. And that right there sets up the entire model. Okay, and this is how you do a joint, universal joint inside LS-Dyna.